is our final review session. So let's take a look at what I've got written up here. How many of y'all actually got a chance to look over the practice test and maybe fill out some of the answers? Yeah, a couple of y'all? That's good. So we have a head start here. So we're going to go through this one by one, though, for those of us who may not have gotten to see it online. So starting out with, we have a couple multiple choice. So the first one is, which of these is not a reference? So we're going to do this by democracy. So how many of y'all think the answer is A? All right, what about B? C? D? All right, so pretty much big support for D, a little bit of support for C. All right, so those people who said it was D, why is D the correct answer? Sorry, what? It's not pointing to anything? And how can we tell that? Yeah, go ahead. Okay, so I like what you said. So there's no address, no star, and it's not an array, and it's not a string. That basically covers all of the clues we've been given to look for at this level as to what is a reference versus what is not. So yeah, that's pretty good. D was the correct answer for all the reasons that you said. If we look back at number one, the rest of number one, we see that for A, we have an int star A. So we're using the star, it's obviously going to be a pointer. We're literally declaring a pointer there, and that all pointers are references. If we look at B, you said that arrays are always references. Why are arrays references? Can anybody answer? Yeah, go ahead.
I know that an array is a pointer of pointers. So I guess that would be, if it is a pointer, then it must be a reference.
Yeah, sounds pretty good. So, you know, an array is a pointer, or at least the first part of the array. The actual name itself is a pointer, and everything else is just variables which we get to via that pointer. So an array itself is actually just a reference. So yeah, so letter B, we're declaring an array. And C, we have ampersand x. So if we remember, ampersand is just our way of finding the address of a variable. So that's an address, falls under our category for references. D is none of those things. It's a very weird looking thing. It looks sort of like we're trying to declare some x that's a pointer type, but that's not a valid way to do it in C. In C, to declare a pointer, you'll always have to declare it with the star notation. It's not a keyword. All right, so let's go on to 2. So which of these is a correct declaration? How many of y'all think it was A? All right, what about B? All right, what about C? And D? Oh, so none of the above? Got like one participation there? All right, so you answered B. Why do you think that B is the correct one?
Because it's saying that a pointer to X accesses the address of Y.
Okay. So, and that's a valid thing to do in C? All right, sounds reasonable. So what about the rest of them? How about A? Can someone tell me why A is or is not valid? Yeah, go ahead. Okay, so we're pointing to a literal. So that's a bad thing. And if we think about that, it makes sense why it's a bad thing. Because a pointer is just a variable which holds an address. And you remember, even though in C we've seen that we print out addresses and stuff like that, they're just numbers where our computer stores memory at. But numbers can vary in what type they are. You know, just like how floats and doubles are 2 different types, addresses and integers are fundamentally 2 different types. So if you try and store one type in another type, you're going to get an error. So here we're trying to store a literal integer into a pointer. And so it's looking for an address, it's getting an actual integer, which is very bad. So that's correct, that one's not going to work. What about C? What's wrong with C? Yeah, go ahead. Yeah, I think that sounds like a good explanation. So it looks like here whoever wrote this was trying to store some numbers into an array. You know, that's our shortcut method for declaring values in an array. We declare the array, and then to the right of it, we use our bracket notation filling in the spots in the array. However, even though all arrays are pointers, not all pointers are arrays. So it's really important to remember this only works with arrays. And here we just have a regular pointer. Now if we declare this as an array, like if instead we'd said maybe int x square brackets 4, then that would have worked just fine because we would be using our array notation. But it's just a normal pointer, so that's going to give us an error. All right, so what about D? Who can tell me why it's wrong or right? Yeah, go on ahead.
Int x is not a pointer. It's an actual integer.
Yeah, so it's an actual integer. So same thing we talked about earlier with addresses and integers not being the same type, but reversed. Here we're trying to store an address into an integer. This might actually run depending on your compiler, but at the same time, it would not be correct because your compiler might do some smart things, try and convert that to an integer for you, but that's sort of like some of the other things we've seen with dev C++. It'll do some smart things and make some illegal things illegal every once in a while. So either way, bad programming practice, don't do that. Really no reason you should ever need to. All right, so that takes care of 2. Anybody have any questions on the first 2 before we move on? All right, so number 3. Which of these is a pass-by-reference function? So this one's getting into more tough stuff. So how many of y'all think it was A? What about B? C? And D? Unanimous for C. Great stuff. All right. So for those of y'all, for one of y'all who said it was C, can you explain to me your thoughts behind that? Why is C the correct answer here? Someone we haven't heard from yet. There's not many of y'all here, so.
Well, I mean, it's a function, so map a pointer to a function is the correct thing, and so the pointers would be inside the argument and of the function.
Okay, so because it's a function and it has pointers inside of the parameters is what you're saying, it's a pass by reference. Okay, yeah, that makes sense. So let's take a look at why some of the other ones are not pass by reference. So if we look at the first one, it's really simple to see that A is not passed by reference. There are no references there. Very easy. If we look at B, it gets a bit trickier. Can anybody tell me why this is not passed by reference? Yeah, go on ahead.
Because the parameter you're passing in, the x and the y, are not references.
Exactly. So.
The only reference is math, and that wouldn't work right in.
Okay, well, hold on just a second on that. So first of all, I really liked what you said, that it's the fact that the parameters themselves are not references. So when we're talking about pass by reference, the important bit is the pass part there. So when you're looking for pass by reference, it's the variables you're passing into the function, which you have to check. The actual stuff outside of the function doesn't matter. So you said that that we couldn't have an int star math. So we have not seen int star math or any sort of int star or float star or char star functions, but those are actually perfectly valid. So if you think about it, what is an int star? Well, it's just a type, right? It's just an integer pointer type. And all it's saying there is that this function is going to return an integer pointer. Now we've actually used functions which return pointers. We haven't really made use of the pointer bit returning, but we have seen them before. So maybe if you want to go back to your notes, look at some of our functions which we've practiced with. I think especially we've probably done some with strings that return pointers. That might be an interesting thing to look at. But it is actually totally valid if we want to have a function which returns a pointer. It's just not something we really see at this level of C programming. But the important part is that here, though, the pass by reference, the references have to be inside the parameter list. Okay, and so if we look at D, we see D's really wonky. Again, we have an int reference math. You know, reference is not a keyword. It all has to be done with the symbols in C. So that takes care of 3. Let's move on to 4. All right. So which of these will not properly declare a structure, assume the structure has been previously defined? So how many of y'all think it's A? What about B? C? And D? All right, so mainly for C there. So let's go through these, just picking out which ones we think are not function or do work first of all. So what about A? Why does A work? Someone tell me. Someone we haven't heard from before. These are the easy ones. You don't want me to call on you when we get to the hard ones. Yeah, go ahead. Okay, so that bracket notation, I like you wrote that down. We have the keyword struct, then we have the type. It's actually a struct student. So the struct student is the full type, and the variable name is Bob. And then we have the bracket notation. So the bracket notation with struct, very important to remember, is a shortcut way to fill in structs. So maybe we can assume here this is a struct. It has a name field, which contains an array of characters, and then it has a float field, which holds maybe, I think it was a GPA when I wrote this. So yeah, so name and GPA. So we have here just a very quick and easy way to initialize a struct. Now, one thing I would caution is to try to avoid the habit of using this. I think your teacher, she put this in the slide, so it's fair game for the test, but she skimmed over using it a bit because it's not the best way to initialize structs. It's actually fairly dangerous, and some more complex structs to initialize a struct this way. For instance, just think about, how would you initialize a struct which has a number array inside of it, or a two-dimensional array of strings? How would you initialize that? The answer is it's not really well defined. So this is why we try to avoid this method unless it's for very simple structs, and even then, it's still not the best. But like I said, fair game on the test. It was on at least 2 of y'all's slides, so you should definitely be able to spot it when you see it. All right, so B. Why is B a correct struct declaration? Anyone? Yeah. Okay, yeah, very straightforward. We have a type followed by a variable name. Easy declaration there. All right. So what about C? A lot of y'all said C is not a possible way to declare that struct. Why not? Yeah, go ahead. Well, we didn't ever say that, so why couldn't it just be struct Bob as the type? What do y'all think? Yeah.
I think it's because you have to have, the type is the struct, saying it's a struct, and then the name of struct is the type itself. So you need a separate variable for the variable itself.
Right, exactly. So you had the first half right in that we were missing something there, and then what's happening is that we always need at least 3 words when we're using our struct declarations. So we have the struct keyword, we have the thing which sort of defines it, like in our instance it's struct student, or here struct Bob. But then even if we just said struct Bob, it'd just be like saying int without putting anything next to it. It wouldn't actually be a full declaration. So we need the actual variable name that the type would go with. So that one's a bit tricky, but you all spotted it all pretty easily, so that's great. So last one, D. Why is D a possible way to declare a struct? Yeah, go ahead.
So it could be a type def.
Okay, and what does a type def do?
A type def basically allows you to declare the structure without actually saying struct before.
It gives you an alias.
Yeah, okay, so those are both excellent definitions. So it allows you to declare a structure's name without putting struct before each time, which is formally referred to as an alias. So it's a much quicker way to write code. It's a pretty nice way too. I know your professor favors it. I favor it. A lot of y'all seem to favor it. So very nice and easy way to make structs a little bit quicker to type out. All right, cool stuff. So anybody have any questions on the last 2 before we move on? All right. Well, so now we have number 5. Which of these is false? So how many of y'all think the answer is A? An array is a reference. All right, what about B? The ampersand generates an address. All right, what about C? The star dereferences a pointer. And D, strings are always passed by value. None of y'all think they're all right? Okay, so some of y'all think they might be all right. Who knows? I should have put an E, all of the above, for all of these. Never take what I say for true. Well, except for here. You can take everything I'm saying here. It's all good. We'll question everything. All right, so for those of y'all who said it was D, D is the incorrect one. Why is that? Yeah, go ahead.
A string is just a char array, and char array, you already have the addresses, so everything is passed by reference.
Okay, yeah, so I think that's an excellent breakdown. So we know that a string is just a char array. You know, it's one of the fundamental properties of strings. And as we noted earlier, array is a reference itself. So, and you know, for the reason that you said, arrays always have an address, so they're always just passed by reference. Okay, so the correct answer here is D. Everything else there is true. You know, we use the star pointer whenever we want to dereference a pointer to get its actual value. We use the ampersand whenever we want to generate an address. And, you know, as we just mentioned, an array is always a reference. So good sort of recap there of most of our reference stuff. All right, so what about number 6? So we have some C code here. Looks like the page cut it off. Oh, no, that doesn't work out well. All right, let's see if I can get that right. Okay, there we go. So we have some C code here. Hopefully all can still read it. Now, you're asked to basically figure out what the output should be. So how many of y'all think the output for this is going to be A, uppercase C? Okay, how many of y'all think it's going to be B? All right, what about C? And what about D? Doesn't compile. Okay, so y'all pretty much think it's going to be uppercase C. So those of y'all who think it's uppercase C, why do you think so? Go ahead. Okay, sounds reasonable. I think that was what all of y'all voted for. Anybody have a different opinion? We're going to test this right now just to make sure. Okay, but so let's put it into our compiler, see what's going on here. Testing.c. So for those of y'all who have come in after I started, make sure before the end to fill out an evaluation. Please put the number on the board in the top right. Okay, so we get something, oh gosh, y'all can't quite see that. So you're going to have to take my word for it. But it is a lowercase c that we actually get here. So, does anybody have any ideas why that might be? Okay, so what you're saying is do this. Okay, so why does this fix the problem? Okay, gotcha. So what's happening here, just to sort of break it down a bit, thank you for the explanation though, so we're calling this function toUpper, we're putting in the lowercase, we're putting in a variable which holds the lowercase letter c. So we know this function actually does take in stuff and make it uppercase. But if we remember correctly, this function returns the uppercase letter. It doesn't change the variable which was put in. So if we put in a lowercase c, it returns an uppercase c. It doesn't actually change the variable which we put into it. So how can we know for sure that the variable we put in will not be changed? By the function. How can we know for sure that the variable put into the function, in this case the variable is a char called c, how can we know it will not be changed by the function itself? Yeah, go ahead. It's passed by value, exactly. So this is a really important thing to check for when you're using built-in C functions. Any function which is passed by value will not modify the content of the variable itself. So if you notice here, we're not passing in the address of C. C is not a pointer. we're not working with any sort of arrays here, so it's not a reference. So it fails all of our reference checks. So it is definitely not passed by reference, it's passed by value here. So we immediately should be sort of thinking at this point, okay, we're going to return something. That's how we're going to change C. So let's test it, check to see what happens. Compiling and running it with this, this code. Let's see. Do you all remember how the professor changes this? She makes the code look bigger. Yeah, it's uppercase C. But yeah, so that's the key there, is that it returns. Oh, here we go. Oh no, I'll work on this later. It returns the value that we want to store. So it's always very important when you're working with those C functions to make sure you've got them working out exactly right. So this is why one of the most useful things you can probably have on your 3x5 reference card, which your professor is letting you bring in, is just functions, what they return, how they work, stuff like that. The C-type library especially is a very hard library to remember all the stuff for. This is one of those C-type functions, the 2-upper. We have a couple others ones we've learned, like is alpha, is number, all basically the character processing stuff. Those can be tricky ones to remember exactly how they work. So they're very good ones to have on hand in a quick reference sheet. You can save yourself quite a bit of time with that. All right. So, does anybody have any questions on the last two, number 5 or 6, before we move on? All right, cool stuff. So, we have an hour left, so I'm going to open it up to question and answer here. Before I do, I just want to show you all really quickly what the rest of the problems look like. And hopefully, maybe these might answer some of y'all's problems. We can go over these as well. So the first one is a short answer, which asks for the output of the above code. It's just a very fancy bit of math where we do pointer manipulation. Not too hard conceptually. Very good, though, for practicing tracing problems and making sure you're really solid on pass by reference. Number 2, a bit more difficult. So we have here a struct, which is a cookie. And then we have a function, which takes in an array of structs and does some stuff. And then we have a main, which calculates some stuff. I don't want to give too much stuff away here, but it looks like it's just doing a bunch of struct manipulation and then doing some math with that. So, and the last thing the main does is it has a menu which allows the user to input some stuff, and then you're given an input which you have to basically calculate what the output will be based on that input. So this is a bit of a more advanced problem. It'll take a good amount of time to sort of work through, but it's all fairly laid out. Its main focus is structs, making sure that you have a good handle on structs and the ability to pass arrays into a function. So the free response for this practice test is a little bit more involved. It's a bit mathy, but I think you all can do good with it. So the idea is that you have to write a program which calculates the area of 2 rectangles given 4 points on a graph, or an XY coordinate graph is the best way to imagine it. So then you have to determine whether or not a rectangle could fit within each other. So this is called object collision for any of y'all who are interested in video game development. So at that point, once you've determined whether or not they fit in each other, if the rectangles overlap or they're isometric, then neither fits inside each other, and then you have to basically tell the user whether or not one fits in the other or which way it goes. So I wrote an outline for y'all. It's recommended that you use this. I would say it's probably both easier to do this way and a little bit harder because there are some tricks you could try and do which would get you in trouble later on if you did them wrong. So this outline sort of made in a way to sort of guide you through practice with structs, practice with passing functions, and some more abstract problem solving. So that's all I have left for this actual practice test. I'm going to open it up to questions and answers now, though. So who has any, just sort of like any question at all from anything that we covered this semester? Yeah, go on ahead. No. So I'm not going to cover those this session. Yeah. Buggy for the rest of y'all. Anyone else? Any questions at all? We have an exam in 2 days. I figured there'd be a couple things. I mean, I'm happy if y'all are all ready for it. It's awesome. But, yeah?
Your teacher gets dynamic memory allocation.
No, we're not that far. Again,
Yeah, my teacher got that. I'm sorry. Yeah, just the things that I don't understand. Your teacher never got.
that's fine. They're definitely the hardest concepts in the course if you do get to them. Not every teacher chooses to, though. Okay, well, if we don't have any other questions, I guess we can go through the rest of the practice tests. I'm assuming that's what y'all want to do, right? Unless y'all are just like very quiet and totally ready for this thing and want to go home. Because I'm going to be here for another hour. So, I would much rather go through the practice test with y'all than just speak to an empty audience. So let's start off then with the short answers. All right, do y'all want to do question 1 first or question 2? Oh yeah, go ahead. The free response. How many of y'all want to do the free response? Anyone else? Anybody very passionate about doing the short answers? 1 or 2? No? Okay, let's go over the free response. So this is definitely the hardest. So since this one, the main thing here is abstract thinking, I would say, rather than any sort of technique. I think a good way to approach this might be to start off with, let's pair you all up, maybe into groups, take like 5 minutes, maybe hash out some ideas, and then we can all get back together, start going over some ideas we have. So try and find make groups of 2 to 3, just group up with the people around you. Like I said, only 5 minutes. You know, y'all can bear socializing for 5 minutes, right? I mean, that's not too bad. And then we'll come back here and try and get started on this, because it is a very interesting problem. So. Yeah, go ahead. So what you're thinking is having 2 rectangles with 8 points for each rectangle? 4 points for, I'm sorry, yeah, 4 points for each rectangle. Yeah, that sounds like one good way to do it. There's a lot of ways we could do this, though. Oh, that's an excellent question. Did I not put in some sample stuff? Do-do-do. No, it looks like I didn't. So let's assume it's hard-coded. We're going to hard-code it in. Well, no, let's just... Yeah, let's just assume we're going to hard-code this in. So we'll have the first rectangle, for our purposes, look like this. Second rectangle will look like this. Oops. All right, that's a good question, though. Okay, so I think it's enough time just sort of get a general idea of where we should go. So, how many of y'all have any ideas of like how to start this problem, how to approach it? Anybody have an idea? Oh, come on, we just took 5 minutes to work out a problem.
If one is equally or less than whatever on both sides, then it can fit inside itself. And if it's equal to or greater than itself.
Okay, so that sounds like a good procedure. So I'm going to start writing down like all the lists of stuff that we're thinking about here. So you said, so find areas, and then what else?
Comparing the areas. So
Oh, okay. Well, yeah, but I mean, like the stuff you said first, like something about like checking to see whether or not they're overlapping, or like just a high level sort of concept here. Anybody have any other ideas? If you're good, things we can do? Yeah.
well, we could have two variables, I guess. Rectangle 1, rectangle 2.
Okay.
And then we could just be a type struct or a type rectangle. Yeah, so just a struct.
All right.
You would have
Okay, so two rectangles. They'll hold all our data. I think that sounds good. It sort of seems to be what the code is hinting at here too. So sounds like a plan. All right. So what else? What else can we guess about where we might go with this? This is a great technique when you're approaching a problem. Rather than just sort of trying to code down as much as you can at first and figuring stuff out along the way, one of the best ways that you can actually approach do a problem which you don't know how to solve is to sit down, take a few minutes, and plot out the way you're going to approach it. Because imagine, there's a very easy to do way to check whether or not one rectangle is inside another, which fails on edge cases. And last time I gave this problem, a bunch of people did it the first way because they just started coding it through, and then when they got to the test case, it failed because that test case checked for the specific edge case. But if you sort of taken some time to think out how this is going to work, it becomes very apparent that you can't do what they just did. So, anyone else? If not, we can start going off this. All right, cool stuff. So we have two objectives for now. We need to be able to find the area, and we need to load in all of our data into the rectangles. So let's create our rectangle structs first. So we're going to have a rectangle box 1 and a rectangle box 2. So let me switch to the code here. Okay. So rectangle box 1 and rectangle box 2. I think these are a fair place to store our two rectangles, which we were talking about, which are going to hold our data. So how can I store in the data here, and what should it look like if our two rectangles are on the board? Anyone? What's a fast way to initialize everything in a struct? All right, curly brackets. So that sounds like a good idea. This is one of those cases where it's okay to use curly brackets because all the data we're working with is really simple, and it's just integers. So if we look up at our struct, we actually see it lends itself to building a rectangle. So we have upper corner or upper left corner x, upper left corner y, lower left corner x, lower left corner y, and all the way down, on the right side as well. So we have 8 different points, and we also have an area. So how can I initialize these rectangles in the curly brackets? What should I put in? Let's say I want to do the big one first, the vertical one. All right, so box 1 dot. We have all these. Yeah, let's say upper left corner x was 1. And then we do this for all the fields. All right, so this is definitely one valid way to do it. I think the faster way might be, though, to use the curly brackets, like was mentioned earlier, because we have a lot of fields here which need initialized. So let's use the curly bracket notation. So let's assume our upper left corner is going to be, it's going to be x1 and y3. So we'd put in 1 for x and 3 for y. All right, and so this is where, knowing how the struct is set up really helps. So then we'd have the lower left corner, x and y, be our next two things. Let's assume it's 1, 1. All right. And then same thing for upper right and lower right. How to initialize a struct? Well, like I said, she's done it once or twice. Actually, I believe only twice in her slides. But it is fair game. So who can explain to me how the curly brackets works for struct initialization? Yeah, go on ahead. Yeah, so 2 really important things there. So the first thing, everything has to match field to field. So your first field is going to be your first spot in your curly brackets. Your second field is going to be your second spot. Your third field is going to be your third spot for all your spots. So, here the 1 correlates to upper left x, which is our first spot. The 3 correlates to upper left y, which is our second spot. So those are going to be automatically loaded into our box 1 at upper left x and upper left y. So this is, as you can see, it's a really useful, quick way to do it. Second thing you said that's really important, we have to have it fully filled out. So we cannot have only part of our box struct initialized here. So if we had, let's say, a name for the box, and we didn't know what the name was until later on in the program, we couldn't use this initialization, or well, it maybe wouldn't make sense to use this initialization, because we'd have to name it something else besides what its actual name is going to be. Or we'd have to leave it blank, and we can't do that because you can't leave a field blank when you're using this type of initialization. That's one of the reasons it's not such a good way to initialize structs, but sometimes, like in this case where we have a bunch of integers, it can be very handy. Anybody have any questions on that, on struct initialization? All right, so let's finish it out the shortcut way. So we have now we have upper right x and y. Let's double check there. Yeah, upper right x and y, and then lower right x and y. So upper right x was 2, and upper right y was 3. Lower right x was 2. Lower right y was 1. All right, so then we have the area. So as we just said a second ago, area has to be filled in if we're going to use this method. So another reason I sort of wanted to use this method is because it goes along with the idea of taking programs and working with them in abstract and critical thinking processes for solving problems. So if we want to use this fast initialization method, we have to fill in everything. So it means we have to put an area for it. So what could we put here in the area field? What do you all think? What should we put? Yeah, go on ahead. All right, 0. 0 sounds like a good idea. What do y'all think? Should we put in 0? So is it possible to have a rectangle with 0 area? No? Maybe. I don't know the actual definition of a rectangle. But if you imagine just a point on a graph, that's sort of a rectangle. It has equal sides, or it has parallel sides on each side. So sort of a rectangle. So 0 might not be our best option, because maybe in some imaginary mathematical system, 0 is a valid area for a rectangle. You know, it's very easy, though, to imagine at least some sort of instance when there's 0 area of some shape. So what might be a less frequently used number than 0 that we can use? Sorry, what? Oh, anybody? Negative number. So it's literally impossible to have negative area. 0 is an edge case, so it's sort of borderline. I get what you're thinking. It's a good one to have. But negative, we're definitely guaranteed you cannot have negative area. So negative 1 is a pretty good number here. The nice thing about negative 1 is you see it a lot in programming as a flag for something which is uninitialized, because a lot of real-world concepts don't have negatives, like areas. So if you want to check if it's uninitialized at this point, all you need to do is check to see if it's equal to negative 1. If you found the area, it'll be something besides negative 1. If you haven't found the area, it'll still be negative 1. So these sorts of flags are nice to throw into your program. All right. So let's keep moving on here. Let's do this. Excuse me. Let's do the same thing for our second rectangle in box 2. All right. So can someone tell me what the coordinates are for box 2? Oh, are you just making these up, or? Oh, I'm sorry. I meant the rectangle I drew on the board. Yep. Oh yeah, go on ahead. Thanks, though.
1, 2, 1, 1, 4, 2, 4, 1.
Yeah, sorry. Specific reason I drew those 2 ones. So, all right, and then we end with our negative 1. Okay, so we got our 2 rectangles, and now we have all the data loaded in. So it looks like next what's recommended by the code is to find the area. So I think, seeing as that's one of our goals on the list, very good thing to do here. So as we have to use this outline, we might as well make use of our find area function. So how do you all think we can create this? We have a find area function. It takes in a rectangle pointer and does some stuff. Oh, and it returns void. What do you all think? Oops. Yeah, go ahead. Okay, so in the main function? All right. What do you all think? Does that sound like a good idea? Anybody have any disagreements with it? Anybody agree? All right, well, it sounds like everyone's content. I think that sounds pretty good. Finding the address of box 1 turns it into a reference, and now we can pass it by reference. All right, so we're going to definitely do that with box 1. And we'll probably do the same thing here with box 2, because we have 2 of them that we want to check. Now we just have to figure out how to actually make our function work so that it computes what we want it to. So let's do, what did I say it was? It was rectangle star box. All right, let's actually write out what our function should look like now. So first question, how do you find the area of a rectangle? Length times width, yeah. So math's not too hard here. So how can I use our box struct to find the length times width here? Yeah, go on ahead. Okay. Sounds like a plan. So how can I use that to get the values we're looking for? All right. Well, so it sounds like that's the right track to go with. Yeah, do you have an idea?
I was gonna say you put in your struct upper left, lower left, or minus struct for lower left,
Okay.
and then I guess that would be put in as like maybe the arrow, because you would have to put in your struct too.
Okay, yeah. So we need to do a struct with some sort of arrow. And so if we want to subtract the upper left point from the lower left point, that's 2 points. So yeah. Okay. So this would give us what? All right, that sounds like a good plan. So okay, go on ahead. All right. Well, let's try and call it something more specific than difference, because we have two types of differences. We have two different things we're actually computing here. You know, we need the length and the width, right? Yes. Yep. So let's sure. Let's call it. Well, let's just call it length and width for simplicity. You know, concise code's always nice, but very easy to read code's usually higher priority. All right. So we have length and width. So which one of these is this? Upper left corner minus lower left corner. All right, so this is the length. All right, and how do we find the width? Oh, yeah. Yeah, go ahead.
It would be almost the same thing, only this time you would be subtracting either the upper left or the lower left from the right side. So if you went with your upper left corner, you would subtract that from the bottom pointer or the arrow to the upper right corner. Yeah, right, and then
Oh, okay, so upper right corner minus what?
the upper left corner.
Okay, upper left corner. Okay, so what do y'all think? This gives us our length and our width? Yeah, go on ahead. Right. So that's really important. So in C, everything's really explicit. That's why we have an x and y different variables for the actual x and y coordinates in here. So we need to specify which ones we're talking about. So length, is that x or y? Yeah, go ahead. All right. So we'll do x here. Was it like this? Let's just see what happens. And what about width? Is it x or y? All right. Okay. So, yes. So that's a good point. That's what I was just about to ask. Because we're multiplying these together, it doesn't really matter. It's more just something I like to ask to see what the answers are. Yeah. Probably. Let's see. Let's see what it actually says up there. So we have, yes, everything capitalized except for the first letter. So camel casing. These are the things you can't see when you're writing without an IDE debugger on, just like in a test. All right, So now we have our y's and our x's. We got our lengths and our widths. Everybody good with this, or? Okay, return length times width. Ah, yes. So what should we do? All right, what do you think? All right, so let's test it out. Let's do a really quick call to this, see if we can get the area of the first box. Yeah, that should all be fine. All right, so let's just do a quick printf here. So if it doesn't work, what should the area of the first box be? -1, yeah. So this is one of the useful things of having an uninitialized flag. If it does work, what should the area be? 6? 4? Yeah, I think that's right. 2 by, oh wait, no, I don't think that's right. So, oh, no, that's right. Yeah, 2 by 2. Yep. Oh, then the data's entered in wrong at the top. That's the problem. These are supposed to be 3s. 3, 1, 2, 3, 3, 1. Yep. Okay, better. So now let's test it. Hopefully it'll be 4. Yeah, go ahead. That's correct. Wait, box 2 doesn't have an area listed. Oh, good catch. Huh. Funny it got mad there. Oh, I see why. Yeah, we should have a lot of errors going on right there. All right, let's fix that. Fix that. Great question. You've never seen it because you're not in Professor Elva's class, but it's an old way of stopping the terminal. It's fallen out of favor in recent years because it's not good for portability. So, yeah, we forgot to put in the -1. We left a hanging comma at the end. Nope, don't worry. It says 4, so it's all good. Area function worked just fine. So we got a 4 back. Sorry, y'all can't see that. Wasn't anticipating this high resolution, but we got a 4. So good stuff. Looks like our area function is all working fine. So, okay, we found the area. We successfully loaded data into our boxes. What else do we need to do? Okay, true stuff. So let's check it, see if the area box 2 is found as well. The area box 2 should also be 4, I believe. There we go. It's 3. Did we enter the data in right? 1, 4. Oh yeah, 3 by 1. 3 by 1. Yep. Oh, I may have drawn the wrong box, but that's fine. We'll do different boxes if need be later on. All right. So that all looks good. It looks like our area function is working just fine. Anybody have any questions so far on what we've covered? All right, cool stuff. So let's continue on. What is left to do here? Well, maybe looking at the rest of the program can give us some hints. Yeah, go ahead. sounds like a good idea. So let's put some printfs here. So the boxes fit in each other. And one of the requirements was that we also give the area of each. So let's also write that out here. And have areas %d and %d respectively. All right. So box 1 dot area and box 2 dot area. All right. And let's do the same thing for the else. Except here, we're obviously going to do the opposite statement. The boxes don't fit in each other. All right. So yeah. So we got our output. So if our compare rectangles function works fine, looks like the rest of it should run just fine. So it looks like we got most of our work done in our main. So what else do we need to do? What's left on the to-do list for this? Yeah. Yeah, true. We need to make our compare rectangles function. So let's look at our prototype here. So it actually, this is a nice outline. It gives you some hints on what should happen. So it says it returns an integer determining which rectangle fit inside each other. So we know a couple things right off the bat. We know it's an int type. It's going to return an integer at the end. We saw that with our if statement. And we know it takes in 2 rectangles and compares them basically to see if they fit inside each other. So now we just need to write this up. So we have our int compares rectangles, and it takes in. There's no S in it? Okay, thank you. Let's just check. One of the few instances copying and pasting is good in coding. All right. So we have this. We also know it'll return an int at the end, so we can write our return there, even though we don't know what's going to go in it yet. So we need to compare rectangles, figure out whether or not one rectangle fits inside the other. So what are some ways we can go about doing this? All right. All right. So let's declare an int, and let's call it flag. It's a good name for a true/false variable. Yeah. Okay. So if the area of the first one is smaller than the area of the second one, it fits in it. Sorry, what? Okay. So what do you all think? What do you all think about that? Yeah, go ahead. That's true. So it won't be true for the larger one. Now, for our purposes, we're only concerned whether or not one of them fits inside the other. It's an excellent point. If we were concerned about the order it came in, we'd have to set up our whole function differently. But for now, it's just good enough to verify one of them fits inside the other. Good thing to keep in mind, though, if we're writing maybe a more complicated function. So what do y'all think? Just compare the areas and return that? Yeah. So what you're saying is then they can fit inside each other. All right. What do y'all think? Okay. Well, let's try it. So let's say if, how should I write this? Box 1. Okay. I'm sorry, could you speak up a bit? Oh, make it equal 1 at the beginning? All right. A lot of ways we can code this up. So what else do we need here? Yeah, go ahead. Interesting point. So if you look here at what we've drawn on the board, but it is true here. So, I'm sorry, you're saying if box 2 is less than, so here we're going to have box 2 is less than box 1. Gotcha. Okay, so let's check that. So you want an else if and then just the reverse. All right. So saving some time here. Or well, let's do it the drawn out way. All right. So like this, and then what do we do if this is true? All right. What do y'all think about this? Will this work? Yeah, go ahead. So just to clarify, mm, right, exactly. It's a little bit simpler than that. So, yep. Cool stuff. All right, so are we good here? Do we just need to return flag? All right, so what's the else statement? All right, so flag is equal to 0. All right, and then return flag. All right, well, let's try. Yeah, so let's try running it, see what happens. All the code looks like it's in place. All right, so when we run it on our 2 rectangles, which we have written up on the board, we get a compiler error. So why did it error on line 35? Oh. What did I miss? No comma? Ah, my bad. All right. Yep. If you all become professional programmers, 20 years later, you'll be working at your job and you'll leave out a comma. I guarantee it. Okay, so here we get an error. So what's wrong here? Yep, of course, it's spelled wrong. I think I got the prototype right. Mm, to the actual one. Let's see what happens here. Yeah, no errors. All right, so here it tells us, I know y'all can't read it, but it says the boxes fit inside each other and have areas of 4 and 3 respectively. So, is that right? Do these boxes fit inside each other? All right. What do y'all think? Is there any way to move these boxes around so that we have them fitting inside each other? Yeah, not really. So barring rotation, which is a whole other thing of geometry, which we're not even going to get into, we can't move these boxes around in any way so that they'll fit inside each other. Think of it like if you're stacking, if you have cardboard boxes and you're packing cardboard boxes within cardboard boxes, these two cardboard boxes could never fit inside each other. Even though this one's area is smaller than this one. I mean, we could break it up into pieces, store all those pieces in here. It's not going to fit because of its length and its width. So we need to go back and revisit our formulas. So this is one of those edge cases which catches with this. It's why it's very good to plan out far in advance how you're going to approach this problem. All right. So here we check to see if box area, if the areas are less than each other. So if one box has an area less than the other box, will it always be true that they'll fit inside each other? No. So this setup isn't going to work here. So we need something more comprehensive. So yeah, question. Yeah, go ahead. All right, comparing their lengths and widths. That sounds like a good idea. What are you thinking with that? Okay, so what you're saying is if both length and width are smaller, and one rectangle has both length and width which are smaller than the other rectangle, then it fits. So what if one rectangle has a length that's smaller, but a width that's not smaller? Then it would fit still? If like we had a 2 by 2 and a 1 by 3? So that's actually the scenario we have on the board here. So we can see that doesn't work. So what about if they had a width that was smaller and a length that was larger? Okay, so both dimensions have to be smaller. So what if the first box had a width which was larger and the length which was larger? No turning, nope. But would one box fit inside another if the first box had a width which was larger and a length which was larger? Yes. Okay. So this is, are there any other possibilities besides those 4 I just listed? Yeah, go on ahead.
Well, if they're equal in length, then they would set the stereotypes.
True, but we defined equals in the problem definition as being not fitting inside each other. Okay. So yeah, good thing to test for though. So is there any other scenarios besides one having a larger width, one having a larger length, one having both larger width and larger length, and one having both smaller width and smaller length? Any other scenarios? All right. So this is basically some very basic Boolean logic going on here. This is stuff any of y'all who are going to take discrete are going to see quite a bit of. It's a very comprehensive way of approaching a problem. You basically rule out every possibility and account for every different scenario which could happen. So that's, I think, a good approach to this problem. So let's write that up. So what will our first condition be? All right, so if box 1.length, oh, we don't have a length. So this is a time where it's might be a good idea to change something else in the program. So what do you think we could change to make this? Yeah, we could. So let's add length and width to the struct. I think this is a super useful thing to have. Let's go back up, redefine our struct, int length, int width. All right. So we have a point where we actually calculate their length and their width, right? Okay. So yeah, so turns out some stuff we computed earlier on is actually super useful. So this is one of the reasons why it's really, really good to pass stuff by reference whenever you can. Because you can see here, we originally passed it by reference. It wasn't that useful. We were only computing one thing. Could have very easily returned that. But here, we find out these two other things we computed are great to store for later on. So we can have the length and the width stored with very little change to our actual setup of our program. All right, so this look good, deal? Okay, good question. Should this be dot or should this be arrow? Okay, so we're working with references. We're going to use an arrow. All right, everybody good so far? Right side of the room. You all have been pretty quiet since we started this problem. Everything good? Okay, cool stuff. All right, so we have stored now the box width and the box area, or sorry, and the box length. Now we can call those very easily later on in our compare rectangles function. So we want to see if box1.length is greater than, or should it be less than or greater than? What do y'all want to do? I don't know. So which one? Equals equals? All right, let's do less than. So like you all said, it doesn't actually matter. All that matters is consistency here. So, if, okay, ampersand? What does ampersand mean? Okay. Okay, so then we set flag equal to 1? All right, so yeah, so it's a useful thing to know, the ampersand. So basically it means both the left half and the right half have to be true for the if statement to go. Otherwise, if either one of them is not true, it won't run. Yeah? What do you mean, an or statement for what? Okay. Okay, so your idea was on point. We're going to use another check there to check to see the opposite. But we could do it in there, but it gets messy. So else if is nice for that. So let's do the next else if with that statement. So what were you thinking beforehand? Yeah, so this is the mathematical equivalent. These sort of tricks save you time on tests. Always make sure to know the equivalencies of any sort of inequality. So like not equals, the same as equals. Less than is the same as switching them, but greater than or equal to, stuff like that. All right. So what else do we have to do here? All right. So what happens if box 1 has a larger length, but not a larger width? All right, so we have our else statement down here. So it'd go into this one would be false, and then this one would also be false. So we jump to here. And then the same thing would happen if it was with width. If box 1 had a larger width but a smaller length, we jump to here. Okay, so yeah, so it sounds like we covered all our bases. So let's try this. Let's see if this gives us the correct answer. I've had a code come out with a smiley face as the output before. You joke, but it can happen. It's happened to you?
Oh, yeah.
Yeah.
I was kind of an array. I went and printed out that array. It just printed out a whole array of smiley faces.
Yeah, it's a thing with ASCII. It's funny to see, but terrifying. So, all right. So here's what the output says. The boxes don't fit in each other and have areas 4 and 3 respectively. So that's awesome. That's what we want. If we look at our boxes on the board, we can see very clearly they do not fit inside each other. So this looks awesome. Let's test it out with a couple other boxes here. All right. So let's try 2 boxes which are on top of each other. So what do you all think? How will that work out? Yeah, go ahead. Sorry. Great question. Who remembers what we used the -1 for? Yes, the placeholder for the area. Actually, we need to update this. It looks like dev C++ has been especially nice here. What do we need to update this initialization with? Length and width. Yeah, so what should we put for that?
Oh, -1 and -1.
All right, and why not 0 and 0?
Because there is a possible length 0.
Maybe. We don't really know, but maybe. So let's get rid of the maybes, though. But yeah.
We use -1 for the area. Why not use it for the length?
Exactly. So negatives are great when you want to do something which definitely can't exist. So now we have, because we have to always, when we use our shortcut, we have to check every field. We have to put something in it. Dev C++ looks like it's especially nice here. It fills it in for us, but you know, we should have every field filled in. All right, let's try it again. So this is when we have the same rectangle. The 2 rectangles are on top of each other. Now, if you remember, this is supposed to say that they will not fit inside each other. What do you all think? Will this work? We'll see. Anybody have any intuition? It'll work? There's a good confidence because it says here the boxes don't fit inside each other. So this is a nice thing about when you rule out every possibility. When you rule out every possibility, there's nothing left that except the possibility which is left. I think Sherlock Holmes said something like that, but it applies here. So that's excellent sort of wrap up to that problem. Anybody have any last minute questions about what we did here? All right, well, cool stuff. So it's time to end the session about make sure you all get a chance to fill out that evaluation. The number is still up on the board. Just write it up at the top, fill in the bubbles and all that stuff. It's super helpful if y'all can do this. Other than that, it's been a really fun semester. I'm glad having you all as a class. Hopefully I won't see any of y'all this summer. I'm sure you all do great on the course. But study hard for your test on Friday. Don't forget to make that little card. I'm sure it'll be super useful. And yeah, that's pretty much it. So it's been a fun semester. Yeah, no problem. Anytime. Which number? I'm sorry, that should be a 56. So 56. Should be a bit better. Yeah, y'all did a really quick time going through that rectangle problem. Last time we didn't get through it. We didn't finish it in time. So these are the sort of problems you want to practice for a test. So if y'all could, I hate to sort of push you all out because I love letting people stick around and study and stuff, but we do have a session in here really quick after. So if y'all could gather up your stuff, make sure you clean your area, leave it neater than you came in. That'd be excellent. I'll be packing up here if y'all have any last minute questions you want to ask as you're leaving. But like I said, just get those evaluations done. Feel free to bring them up or leave them on the tables. We'll be collecting them. And yeah, that's pretty much it.